Okay. Hello. Hello. Okay. So my name is Wanjala Frida. I think I've met so many of you in different meetups, and I'm so happy that you guys have come out to win this money. All the best. But then for me, I can't take part because, well, for reasons Alfred knows. So a caveat, whatever I'm going to present today, it's not as a solution. So like, you can't say, let me just take Frida's code and use it to, I don't know, do the challenge. No, I haven't done it exhaustively. So I'm just doing it just to demonstrate the machine learning project workflow. So, okay. So I work at Mkopa Solar. I'm 4 months into working there as a data scientist. Well, people ask me whether I fit predictive models all the time. That is no. As a data scientist, you are posed with different business problems that you can solve differently. Some of them, you need to build predictive models. Some of them, you just need to do some really good data visualizations. Some of them, you need to do some piloting. So for today's challenge, we are going to do predictive modeling, of course. And like the main question for today is, how can we use machine learning to identify patterns and relationships between the variables that we have in our data set and help Sandy make a very important decision? Machine learning projects, most people use something called CRISP-DM methodology, which is a structured approach to planning an ML project, and it has different phases. So the main ones are like understand the business problem, understand the data, prepare the data, model the data, and then deploy the model. So I'll be talking through each of these steps today, and then I'll be using the R programming language to showcase how to achieve each of these things. So the first step for any machine learning project, of course, understanding the business. What does the business want to achieve? So I think Sandy have already presented like what their problem is. So it's upon the data scientist to make sure you understand the business problem and then translate that problem into a data problem. So for instance, like their problem is, how can we make our services reliable, reduce the cost of doing business through improved resource management and planning for order scheduling? So most times, business will give you that problem. They won't tell you which variables to use, which data to use, but then you guys are lucky today, you have data, you have variables, you have a data question. So the data question is, can we predict the estimated time of delivery of orders from the point of pickup to the point of arrival at the final destination? And I'm going to follow these steps as I look at the data and try to come up with simple models. So the first one, of course, before you begin, once you understand the business problem, you convert it into a data problem. Because understanding the business problem is really important because it gives you an idea on some of the variables you can use in your predictive modeling. So the first step we are going to do is, of course, set up a work environment in R. The next step is like we need to clean our data, transform it, and then explore the data. I'll develop some features based on our own intuition, based on our understanding of the logistics of Sandy, based on even literature review. Like there are so many ways to come up with features. That's why understanding the business problem is really important in this case. And then once we're done with feature engineering, we're going to do model building, which will involve tuning parameters for our models. And then we're going to evaluate our model using different metrics so that we can come up with a very predictive model that is with a higher level of accuracy. So the last two steps, we won't do them today, but they are very important steps in any machine learning project. So the second step is data understanding. So what does it entail? Collecting your data that help you to achieve objectives, assessing its quality, transforming the variables into their correct formats. So the first step as a a data person is, you have the data in place. So I need to define some dependencies I need to use to analyze my data. So if you use R or use Python, there are some modules that you need to load into your workspace to help you achieve your objectives. So for instance, in R, there are a set of packages that we are going to use today. So I just talked through a few of them. So of course, there is the data management aspect, the cleaning, creating new variables. So tidyverse is your package, is your go-to package. It's an umbrella package with so many other packages inside, like tidyr. It contains dplyr, ggplot. And then we have the lubridit. That is for just working with the dates. And then another one that's very important is the caret. Caret is a set of functions that makes building machine learning models very easy and fast. And then, of course, we have like the random forest for building random forests. We have the XGBoost for building boosted trees models. So it's upon you to decide like which packages are you going to use in your project. So of course, once I define my dependencies, I install my packages and load them into my workspace. So the next step is, of course, import the data into my workspace. So as you can see in this step, I'm importing the data set and then assigning it to the sendy_tbl object in R. Then, of course, I have my data. Then what do I do next? So the next thing I need to do is explore my variables. Like, look at the sendy data that they gave to us. And I love using this function called glimpse. It kind of just tells you how many observations you have, how many variables, the names, and the type of variables that you have. So this gives you a very good picture of your data. And what do you look out for in this step? So in this step, I can be able to see the variable types. For instance, if, for instance, I see a variable like temperature, but then I see it's of type character, that is weird. That's something wrong I need to correct. But then if I look at my data, like everything is in its correct format. You can see the time. You can see the DBL is for the double data type. So CHR is for the character data type. So from here also, I can also even start thinking of the features I can use in my modeling process. Another thing, if you want to look at more detailed statistics of the variables, you can use another function called describe, and then in brackets, the data set you're going to use for your analysis. And then these variables, if you look at the names, they have spaces, they have brackets, like they're not really friendly to use. So what's the first step you need to do? Of course, rename them. So in this step, as you can see, I'm using some of the string matching functions with the GSUB, asking it to look for any space, look for any brackets, equal sign, hyphen, and replace them with nothing. And if you compare the original variables and the ones that I have right now, of course, these ones look much easier to use because all the spaces are gone and I can easily extract a variable if I need to use it at any point in time. Okay, so my variables are okay. Then I need to look at the variables. Like for instance, there's a variable called weekdays, and the variable is a numeric. So in this case, I can decide to change it into a factor variable because it's not ordered in any way. So I can use it as a numeric variable. So one of the ways I do that, like just say, like use the function factor in R to change them into factor variables. And if I look at the new variables, I can see they are FCT, which are factor variables. So also some other variables like personal or business, that is a platform type that were in character format. And just remember that if a variable is in a string format, you cannot use it in any modeling exercise. So you have to change it to a factor format before you use it for any modeling exercise. So I think the first part of just looking at our data set, understanding the variables, changing their format is done. So our next step is like prepare the data for analysis. So one of the ways you can prepare data for analysis is generating new variables. So for instance, what is our outcome variable in this case? So I look at the data set, I notice like Zindi already provided an outcome variable, but then they also gave us the time from pickup and then time of arrival. So the only thing I did here is kind of to check whether if I compute them manually myself, and I compare with whatever they have given, are they the same? And as you can see, yes, true, they are the same. So I can go ahead. Like, are there any other features that I can create from the variables I have that can improve the predictive ability of my model? So I just thought probably I can compute the time from placement of time from placement of the order to time the pickup time, because there could be some delays and maybe they could have some relationship with the delivery time. You never know, just because at this point you're just kind of throwing in ideas of the things you think can affect your outcome variable, but then during the modeling you can drop them out if you feel maybe they're not predictive enough. So I create one variable. So the next step is explore my data. I'll clean the data set. I have getting some new features that I think maybe can affect my outcome. So what the next step is explore my variables. And the main objective of exploring variables is to identify any anomalies. Are there any interesting patterns you can see or relationships between the variables you have and the outcome? So this one helps you kind of come up with some initial insights that you can, so if you are in a work setting, for instance, like every step of analysis, like me as a data scientist, there is a stakeholder who is going to use my model in the activities. So anytime in any step of my analysis, I meet them, I'm like, okay, this is what I'm finding so far. Like, what do you think? They can give you more ideas of what they think because they have better domain expertise about the problem you're trying to solve than you. So here I just plot a histogram to show the distribution of the outcome variable. That's the time from pickup to arrival. And as you can see, it's positively skewed. But then something weird is we have times that are close to zero, like 1 second. Like, is it possible for someone to deliver a product in 1 second? Well, I don't think it's possible. So like, it's upon you now to start investigating, like, why am I having a 1 second delivery time? So with this one, you can talk to the data engineers or talk to the people who collect the data, like, why do you think we have 1 second? Is this something, a measurement error? Like, what happened in this case? So once you find the reason as to why you have like 1 second delivery time, you can think of like, now how can I correct this? But in this case, we don't really know why we have 1 second delivery time. We can decide to drop them. So I set up a threshold of 2 minutes, like maybe an ideal, well, maybe the earliest time we can take to a deliver product maybe is 2 minutes. So I dropped any delivery time that was below 2 minutes. Okay, that's the ones that were above 1 minute. So the next step is I want to do some descriptive statistics of the numeric variables in my data set. So in this case, I pay attention to the minimum values, the maximum values, the mean and the median to see whether my variables are like they have a very wide range, for instance, or we have abnormally high values or abnormally low values, or maybe my data is not normally distributed. So for instance, if I look at the mean and the median, if those two are the same, then my data follows a normal distribution. But then if my mean is larger than the median, then of course that is a positively skewed distribution. And you need to think of ways of correcting for that. So in this case, I just took all the numeric variables, then computed the minimum, maximum, median, to have an idea. Like for instance, the placement month, I expect the maximum to be 31. So if I see a value of 60, that's an error that I need to sort out. Something else I can see from this data is like the number of missing values, for instance. So like temperature has like around 4150 missing rows. And then if you look at the precipitation in millimeters, it has a lot of missing values, which is something probably you need to go and check, like why do we have missing values in this variable? Does it mean something? It could be probably it's missing because it wasn't measured or there was an error in the system, or it means something. So for instance, like someone might say, okay, because the minimum precipitation in millimeters is 0.1, we do not really have a zero. We don't have a zero in our data set. That means probably if it's missing, maybe there was no rain that day. I don't know. It depends. But you have to confirm this with the data engineering guys first. We have other variables like time from pickup. The minimum is 121 now after dropping, and then we have 7,000 seconds. So what about the factor variables? So people call them factor variables, categorical, discrete, whatever. So in this case, I just want to see the distribution of each of the levels of the factors. So like R has a very easy way of filtering your variables, just is.factor. Then using this map function from it's a package called par, I can be able to generate statistics for so many variables at the same time. So in this case, I have how many variables? Around a number of variables. The first one is the platform type. So we have 4 levels, but then unfortunately there was no description of these platform types. But as you can see, level 3 has like a really high distribution. So sometimes you might it shows that this variable is not doesn't have enough variability, enough information for you to use in your modeling exercise. But then there's no rule of thumb. You just have to decide, like, I think 80% like is just too high. So this variable is not variable enough. I can drop it for my analysis. Another one is business or personal, or I think it's the customer type. So you can see like most of them are from the business type. So you can look at the other statistics from the other variables, and then it will give me some idea on how they're distributed and how they can affect your output. So the next step is to check for missing values. We've already seen them earlier in the first table, but it's just a function I love using to check for my missing values and make a decision whether to drop them or to continue using them. And we only had 2 variables that had missing values. That's the precipitation in millimeters, like 97% were missing. Well, just too high. Well, for me, I'll drop it. But then someone might say, okay, missing precipitation means 0 rainfall. Probably they can impute with 0 and then fit their models. But clearly, I dropped it. And then for the temperature, only 20% are missing. And there are different ways of solving missing values. You can impute them. You can drop them. You can impute them using like the mean or the median, or you can impute using some prediction techniques that are available. So in this case, I just replaced the missing values with the mean of the non-missing values. Because most of the, like all the machine learning algorithms, they don't know how to deal with missing values. Like you have to look for a way to either impute them, drop them before you feed the data into a machine learning algorithm. So right now, my temperature is imputed. I can look at the distribution, it looks normal. Another thing to look at is outliers in the data set. So outliers are very interesting. They could happen because of so many different things. System issues, measurement errors, or it could actually be true. Someone just took a long time to deliver a product. It could be true, for instance. But then, so of course, you have to make a decision. What do I do about these outliers? So there are so many different techniques of dealing with outliers. Some will say, okay, let me set them to missing and impute them. Let me drop them. Or let me fit a model with and without the outliers and see whether there's any difference in the output variables. So the decision is in your hands. So I just did a box plot of one of the variables, the distance in kilometers. And for numeric variables, you can determine outliers visually using a box plot. And as you can see, we have outliers in our data set. So what do we do about these outliers? Do we drop them? Do we impute them? Do we just keep them? So in this exercise, I just kept the outliers in the analysis. So the next step that I did was to assess whether there's any relationship initially between the variables and my outcome of interest. So in this case, I took a few numeric variables and computed a correlation. This just gives you an idea on the strength of the relationship between the 2 variables and their direction. So an example is like, if you look at the distance and the temperature, the relationship is positive with the delivery time, which means like the longer the distance, the longer the delivery time, which makes sense. Yes, makes sense. So the next step is like preparing our data for the model building exercise. We have already created new features. So this step actually is a very short step where I just select the variables I want to use in my modeling exercise. So the variables I select can be motivated by the what insight I've gotten from the data exploration exercise. And from here I just picked around, how many variables are here? Around 5 variables for my use in the next step. And then for the categorical variables, I created dummy variables using some really nice package called Fast Dummies from R. So once you have your variables in place, so the next step, of course, is the modeling exercise. So for R, if you want to fit models so fast, there's a package called Caret. And as a data scientist, you need to spend a lot of time in the previous steps I've just talked about, exploring your data, cleaning it, getting new features. The modeling step is very short because a model, like what breaks or makes a model depends on the features that you have. And of course, also the model you're going to use to fit your model. So there's a concept in machine learning called the bias variance trade-off. So the idea is to minimize, like to kind of find a middle ground between the two concepts. So bias literally means underfitting. And then variance means your model is overfitting, so you can't generalize it on new data. So you wouldn't want to have a model with high bias because it hasn't learned from the training data really well. So it can't really it doesn't have the ability to predict on new data. Or you can have a very good predictive model, but then it cannot be used to generalize on new data because it has overfit, because you used a very complex, for instance, a very complex and flexible model. So an example would be, maybe I'm comparing a linear model and maybe a polynomial model. So a linear model is not flexible, but then a polynomial or maybe a neural network is very flexible. But then the problem is a linear model will have a very high bias, but the polynomial will overfit and have a very high variance. So you need to look for a middle ground between the two concepts. So let me just go through the steps you need to use before you start modeling. So the first step is shuffle your data, because sometimes the data is ordered in a specific way. So for instance, like certain data set might actually come in ordered by the order time, which is not good for your modeling size, so you need to reshuffle the data set. So the next step is you need to split the data into training and testing. So the training one is the one you're going to build a model. Then testing, just testing how good is my model that I built on the trained data set. So R has a nice function called create data partition from the Caret package. So you need to decide. Most people will be like 70% training, 30%, 25%, sometimes it's upon you to decide. Other data scientists, actually it's recommended that you need to have 3 splits. So you need to have the training data set, the validation data set for tuning your parameters, and then the test data for now evaluating how good the model is. But in this case, since we are going to use the Caret package, the Caret package literally auto-tunes parameters for you. It also, it's very fast, of course, very fast, and also the fact that you don't really have to pick the validation data set because it's going to do validation within itself. So I think we'll talk about that when I get to that position. So the next step is model selection. So you need to ask yourself, like, is our problem we're solving, is it supervised or unsupervised? So in our case, it's supervised. So if it's supervised, is it a regression problem or a classification problem? Since our outcome is continuous, that's a regression problem. So you need to decide, like, which models can I fit on a regression problem? I cannot do a logistic regression model on a continuous outcome. That's not allowed. But then so I need to define, like, beforehand, which models I can use. So in this case, there's a linear regression trees, or support vector machines that you can use in this case. And then I'll talk a little bit about the evaluation metrics. So when you have a continuous outcome, there are around, I think, 4 5 metrics that people normally use to evaluate how good your model is. So the most common ones are the root mean square error, and then the mean absolute error. So I want to discuss the details because of time. But then, so the metrics, like RMC is very common. It's very common. But then, mean absolute error is very robust to outliers. So you can use either. But then the thing is, like, RMC is always equal or higher than the mean absolute error, because when you have outliers in a data set, it penalizes for that when it's computing for this metric. So Caret has around 238 models within it that you can use to fit your data. I've just displayed like the first 20. So if you want to look at the parameters of the different models you want to use, so for instance, like for the linear regression model, which is the LM, it only has the intercept. When I look at, maybe I'm using a random forest, maybe I'll have a number of trees, I'll have the maximum number of features to use. So those parameters are the ones that you need to know beforehand so that you can be able to tune them to make your model more predictive. So let's start with a very simple model, linear regression model. So this is how the Caret package works. You only need to supply the training data set, supply the method you are using to analyze your data set. So in this case, it's linear regression, so I'm going to use LM. And then the TR control is used to control for the cross-validation. So in this case, cross-validation, you have to define how many folds you need to use. You can use 10, you can use 8. You have to decide. So this option, verbose iteration, just tells the package not to display the whole process, because sometimes it just be printing whatever it's doing, and maybe you don't want to see that. So once you fit your model, then you're going to have the output, of course. So the output will just show you the evaluation metrics. So as you can see, we have an RMC of around 764, and then the MAE of around 533. So you use this to compare different models. So the next one, I wanted to fit a support vector machine, but it was taking too much time. But then you can try fitting it. And there are so many different kernels you can use. You have the radial, linear, and polynomial. So try different ones. The random forest, also you can try it. But the problem with Caret is, not problem, but the thing is, random forest has so many parameters, but then it can only tune the mtry parameter, which is the number of maximum features. So you need to make a decision about that. And then another one is the boosted tree. So I just fit linear model and the boosted trees. And then now I have the metrics. So the metric here is RMC, and then I have MAE here. So the next step is I need to compare my models. So this graph clearly shows me the dot here is the estimated root mean square error. So the lower, the better. So according to this graph, the boosted trees has a lower root mean square error. It also has a little bit lower variability, because if you look at the length of this confidence interval, it's so large compared to the boosted trees one. So of course I'll go for the XGBoost, given the fact that it has a lower RMC and also like less variable. So once you choose, so you can fit as many models as you can, and then just come and plot this, and then you can decide which model you're going to use from now on. So once you select the model, test using a test data set, submit the file to Zindi. So I might not really be able to show you how to submit the file to Zindi, but Steve will show you how to do it. I hope you learned something. And I'll be around the whole day in case someone has a question. Many minutes.